Hi, my name is Norm Kirchner. In this demonstration, we're going to be talking about high-speed characterization of an X-band transmit-receive module for the purpose of radar systems, ASA systems, and beamformers. So within the system here, what we're doing is we're characterizing this chipset of basically a gain phase array along with the transmit-receive module from analog devices. That's an 80AR, 1000, and 80TR, I think 1107 or something like that. I can't remember offhand. But in order to characterize a chipset like this, you would want to be able to indeed still do your S parameters so you can check your stimulus and response, but also you want to be able to check the gain and phase stability as you're sending those digital command words to the individual device. And so that's what we're doing here with the NI system that we have. We have our vector signal transceiver along with the vector network analyzer in line with it that you can see clicking along there. Both of these connections are going to both sides of that transmit-receive chain. And then what we're doing is we also have our DC power. We have five different voltage rails being supplied here from our modules. And then our basically our SPI digital control in the chassis as well. And so that's really the instrumentation that we have here. Of course, in PXI, it needs a computer, so we've got our embedded controller. And that's basically the system that we have connected to our transmit-receive, our X-band transmit-receive beamforming system. So as we know, one of the first things that you might want to do in terms of characterizing your device or your component, you might want to use your venerable VNA to go ahead and check that out. Well, within the past year, NI has released our 5633, our VNA, capable of going from 50 megahertz up to 26.5 gigahertz within a single slot within the PXI chassis. And so really that's what we're looking at here. We have the ability to look at the performance of the device, and what you're seeing is basically gain and phase changing as we're sitting here staring at it, but that's because we're actively going through, as you can see in the lower graph, constantly changing the configuration of that, basically the gain and phase shifter, the beamformer, if you will, device. And so as that's changing, we're seeing some updating on the graph here overall. And so this is via Instrument Studio or out of the box, no code interface. So you can just put in a VNA, open up the software, and you're up and running, no programming necessary, as we have for all of our RF devices at this point. But one of the things that you can note here is it doesn't necessarily seem to be performing as fast as what we're controlling our digital device. And so when it comes down to really being able to open up the speed of the system, as any time that you're in automation, you really want to be able to get all the way into more of an automated program where you can really see that true performance of the automation that you've got. And so what we're showing here is basically the same information, where it's the transmit bandwidth, basically the S21, and then on the other side it's the S12. Now it's a transmit-receive module, so it would seem silly not to switch it in the other direction and look at that performance happening in the other direction. So indeed, so once again, we're looking at both ports at the same time with a single connection to our device under test. Now, one of the challenges is that you can only get so much information so fast from just using a VNA. And so as modern VNA vendors have done, they've kind of shoehorned more functionality into modern VNAs. Well, we're going the other direction. We've already got an exceedingly capable vector signal transceiver that has the ability to give us time domain information and do coordination with other instruments in the system. So I'm going to go ahead and stop the S parameter analysis, which you can see it's taking some time to execute. But if we were to really turn the screws on the system using the vector signal transceiver, giving it a second here to go ahead and kick it into the mode and go ahead and set it into the TX path. So once it starts generating here, you'll see very, very quickly, go ahead and scale appropriately, that we're indeed still sweeping across all of those gain stages and the phase stages, but you're not seeing it basically update here because it's going so fast. Basically, we're able to perform this entire sweep with an acquisition time less than 150 microseconds. And so what that's actually doing is giving us the ability to do more positions in fewer amount of time with the same degree of insight. Now, granted, this is at one individual frequency, but you should be able to sweep that individual across all those individual frequency points because you don't need all the ones that you might get your S parameters from. And you should be able to get exceedingly high performance with exceedingly stable results. And so if we look over on the right-hand side, you can see we can kind of look into one of those individual points in terms of gain and phase, and we can look at the stability basically going through the device itself. So thus giving us a full characterization, not only of like say the return loss or your S parameters, but also being able to give you very, very specific insights into how the device is performing. Basically, if you look right here, this is basically showing us how much the device under test is being basically varying per individual phase stage. So basically, I think we can kind of zoom in on that there, and you can kind of see from one stage to the next. Let me go ahead and zoom out. There we go. So if we wanted to, we should be able to look into here, and you can see that for that individual stage, basically as we move across, you can see we have different amplitude stages as the device is changing its phase. It's a very critical piece of information if you've got an active electronic steered array, because you want those to be as flat as possible. So the ability to get that information in time as fast as possible can give you a lot of extra insights in terms of the performance of what you're looking at. So really, the last part to really note is that within the system here, because we've got time domain, frequency domain from the VNA, and digital control, we can actually go full coordination where there's no real software commanding and controlling of the individual instruments. We've asked them, digital instrument, here are all the commands that we want you to send that are going to give you the ability to move between each one of those positions. Analog instrumentation, every time that you get a signal from your digital device, take a measurement. And then basically the digital device is waiting for the last sample to be acquired, even before we're through processing it, telling the digital device to move to the next location, basically in the array that you see here. So basically the ability to move around that. And so what we've done is we've hyper automated the overall process of digital and analog coordination so that we can get the acquisition and analysis times of this overall system down to a staggering sub 50 millisecond for the entire, basically, kind of all the characterization that you might need from the beamformer itself for your individual conditions.